So this work is done under the Intel Parallel Computing Centers. So I guess most of you guys don't know what is quantum Monte Carlo method. So I will give a quite quick overview. So we have a lot of methods to simulating materials at different scales. So when you go down to the atomic scale, like you have molecular dynamics, if you further go down into smaller scales, you will have to deal directly with electrons, and a lot of features has to be described with electrons. So in this field, in this method, we should usually call them electronic structure method. And they have features that when you go towards more accurate, towards accuracy, actually the computational cost associated with it grows dramatically. And the system size you can simulate reduces a lot. So you could see like from 50 atoms with those couple cluster or in configuration interaction methods towards tight binding method, you might get like 100,000 atoms. So our QMC actually sits here. It has it's more expensive than a lot of people doing the DFT, but somehow it has way better scaling than those methods, and we are able to do some reasonable material simulations at this level. Yeah. Then in these methods I mentioned, electronic structure method, the main goal is just solving the many-body Schrodinger equation. So as a cheap method, you have density functional theory. It's a mean field method, but it's cheap and it can be parallelized on HPC, but somehow due to its theoretical limitation, it's hard to improve, and it doesn't have the built-in support for like strong correlated electron systems. And if you go for the quantum chemistry method, which is usually very expensive and like very hard to get the solid working, and also it's bad on the HPC world. The method we use, quantum Monte Carlo, actually it's accuracy, systematic improvable, and you can easily parallelize it. So for this reason, as the computer gets more available, we kind of have more opportunities to use this accurate method. So the main method we use, quantum Monte Carlo is a collection of Monte Carlo method for quantum mechanics. But the main algorithm we use is the diffusion Monte Carlo. Here I give schematics to show you that how it works. So basically, it's called Monte Carlo, so you could understand that it's mainly, you are mainly doing decoupled calculations on those Markov chains. So for example, this is a chain, actually. So with a start configuration, you do random walking. So do random walking based on your master equation, then you get new configurations. And in principle, you could go as long as you want. However, since the significance of those chains will change, and to retain the efficiency, and so we have to remove the small weight chains and duplicate the large weight chains just to get the load, and then also to correct the load balance. So there's some communications you are required at this step. So this is a chain, and we call an individual unit as a walker. This is the algorithms, actually. The pseudocode, you will find, as I mentioned, the walker is at a very high level as a parallelism you can expose. And actually, we use it a lot. So if you do, you can easily distribute it across the MPIs. You get almost ideal scaling on the weak scaling side. Then there's another concurrency you can expose. It's hidden here. This part has very heavy computational cost. So if you could expose this concurrency, the concurrency is order n, so n is the number of electrons. So if you can use it, like to do it on SIMD, you will get huge benefit. This has been exposed to GPU already in our code. So in QMC pack, the workers is not only distributed on the MPI, but also we distribute it across the threads using the OpenMP, or we distribute across the SMs using the CUDA for the GPUs. However, as we need to get our results as soon as possible, nowadays we are using way less, sorry. Okay, let me finish that one. So on an inside MPI task, you can have multiple workers. So then you can distribute them across the threads. But as long as we want to get the answers as quick as possible, we just reduce the amount of workers. But there's a limit that we have to do 1 worker per thread. So in this regime, we are now stuck because the frequencies of a single core doesn't improve. And however, the nodes get fatter and fatter, more compute power is integrated on nodes. So if we can better improve the utilization of those cores, so it means we have to go beyond the 1 worker per thread, we can get performance. So you have to work hard on it. This is quick recap. So I'd like to remind you a few specs between mainly comparing the KNL and Blue Gene, because at Argonne we currently have the Blue Gene, and the KNL is the next the coming system we are going to use. So there's trivial things like you have 4 times the amount of cores, but the non-trivial things is like your vector unit. For each vector unit you have, on Blue Gene Q you have only 1 vector unit, but on KNL you have 2. And also the number of flops for each unit you can deal with, you will find it's a factor of 2 or 4, depends on if you use double precision or single precision. And then another significant change is the high bandwidth memory. So if you just roughly compute the bandwidth with respect to the DDR on Blue Gene Q, you get about 10x. If you compute the double precision flops, it's about 13. So we'd like to see the performance of our code on KNL. So if, the simplest way is just get your code, do nothing, and check the raw performance and see what kind of information we can extract from it. So we are doing this experiment running on the titanium dioxide systems. We found actually if you are doing if your system, your calculation memory footprint can completely fit into HBM, it's very well, we just do the cache mode. There's no difference between cache mode and the flat mode. So yeah, this is what we found. Then if we compare the core-to-core speed up, so these are the KNL, this is the Blue Gene, we got approximately 2.73 in this way. So we are a little bit off this 3.24. So based on the previous slides, I can directly compute it. But it's OK. There are a lot of rooms we can do further. So then if we compare the node-to-node performance, we found that we only get 3.32. So if you compute this number multiplied by 4, the amount of core counts you have, you will find actually we are below this number, because now, as I said, I have to do 1 worker per thread. As I increase the number of workers, the memory footprint goes large, and clearly it goes out of the HBM. So for example, for this reason, I cannot directly run the flat mode, shuffle the data into the HBM. So for the memory issue, we are limited the bandwidth now. So the performance, we didn't get this projection number. So we'd like to see where are the components that's loading down our code. So we have quite a lot of experience with profiling the code, and the information is clear. So these are the kernels associated to the physics, and these are the distributions of them. So this is from BGQ, but I have also the numbers from KNL. So by comparing the KNL and BGQ numbers, we clearly see like the distance tables, we are doing terrible here. It should not be that slow, simply because this part is almost scalar. We didn't get any vectorization on that. The cubic B-spline is small. It used to be very expensive in the past, up to like 60% of your calculation. But during the past years, we kind of work hard on to nail down this number, and now it's quite good. But somehow, when we know that this part we have some vectorization, but not really doing in the ideal way for KNL. But when we solve the problem of those, this one will show up again. So it's really important to look at this part. So the inverse update is mainly a BLAST2 calculation. So actually, we get a lot from the get benefit a lot from the high bandwidth memory. So the BLAST2 is memory bound, not compute bound routines. Yeah. So after this quick study, we look at the status of QMC pack. So we know that at top level, those parallelism handled through the Walker level is pretty well, so we don't need to care about that much. However, there are a lot of potential places we could improve. So we know that currently our code is mostly in double precision, except certain portions we have handled to use single precision because to cut down mainly to cut down the memory footprint. But the other place there's all double precisions, and for the SIMD efficiency is low. The reason is simply because in the past we do try to use the OOP in the best way we can. So somehow we wrap all the data in kind of array of structures. So you typically see like distance, coordinates like this, and gradients like this. So it's not so good for vectorization. So we should solve this problem. Overall, on the code, there's a vectorization only in those two parts. So actually, there are some, QPX is the vectorization for the IBM Blue Gene nodes. So we used to do that, but this is not done in a very nice way. I will talk later. So we take two routes. So one is from the top down. So we try to use more synchro precision in our codes. The reason is clear. The hardware could do more. So if you look at the Xeon 5 or the GPUs, you will find that you can't, how to say, resist the temptation from the single precision. Even like on Blue Gene Q, the floating point unit does the computation always in double precision, but there are other benefits. You could reduce your memory bandwidth demand, and also you could reduce your memory footprint. So it's still beneficial to do it on BGQ. For reducing the memory footprint is also important for Xeon 5 for the HBM. In the past, in QMC pack, we learned that the GPU accelerate parts, they are mostly done in single precision. So it seems fine. As long as you handle the critical part with double precision carefully, you can mostly use single precision, and you get huge speed up on the code. For example, K8 is 2x. So you have to try to port the code to single precision. So we did the single precision, introduced single precision in many places of the code, like the wave functions, the Hamiltonians, calculations, those parts, and also the distance tables. We do it in single precision now. So the benefit here is, so these are the columns paired. The bars are paired. So one with the double precision, one with the carefully tuned mixed precision. And the blue ones are on the KNL, and the yellow ones are on the Blue Gene. So when we have small code counts, actually we only see about 20% faster the code on KNL. There's a clear reason, because the vectorization is poor. So you should not expect like the 2x directly from changing the precision using more flops. But there's again like the memory bandwidth things you can always get from it. So that's why we only get 20%. We expect when we do better vectorization, this benefit will even be larger. So if you compare like a 4-node, so you will see like 50% faster the code. Clearly, the memory bandwidth is playing there. Okay. Actually, so you like especially like using hyperthread, you find like if you don't do it, if you like use up all your memory bandwidth, your performance never goes up. You use more hardware threads and nothing changes, as actually your performance goes down. But as long as you improve the memory bandwidth in this way, so you still gain performance there. And surprisingly, we found that even on BGQ, because in the past since there's no single precision float point unit, we were not so motivated to use the mixed precision. But actually, we found when we have it, we gain about 70%, which is huge for the bandwidth. I think it's mainly for the memory bandwidth. Since we will have the machine for a while, so we simultaneously get benefit even on our old systems. So the other route we deal with our code is to do the top-down method, the bottom-up method. So we know where are the corners, and in the past we tuned some of them for BGQ, but with QPX intrinsics, which is somehow the algorithm is portable. We know how to make it portable, but the implementation, we are limited by the intrinsics, and we cannot directly use the implementation. So the main method we do is to change the array of structures to structure of arrays, which is we actually used in the BGQ implementation, but this time we goes beyond that. Then we also introduce the array of structures of arrays. So it's tiling. I will explain details later for this optimization. So we are not directly working on QMC pack the whole code. We do it on a mini app called micro QMC. And as I mentioned, the intrinsics is a big problem. Now we have the OpenMP4, so we can simply deal it with this OMP CMDs. Then, of course, there are a lot of attributes you have to add properly to get the performance right. So this time I will focus on the B-splines evaluation in the code. As I mentioned, in the past it takes about 60% of the time, and now on BGQ it's about 10. So it's really beneficial to work on it for the vectorization. So let's look at the computation. It's mainly interpolation. So if you have a function, so this is an orbital or a wave function, then you have it over the 3D space, real space. What you do is, so like DFT codes, like plane wave codes, you directly compute based on the plane wave coefficients, but we don't do it. So we need, because we are evaluating those phi r, the values over and over again, we want some constant cost rather than plane wave that increase as your system grows. So what we do is you do an FFT from the K-space to real space, then you just spline the wave function on a mesh, on a 3D mesh. So that's why, then when you need a specific value at certain location, you just interpolate it. What we do is, so in X, Y, Z 3 direction, you find the nearest 4 points, then you do the interpolation based on this 4x4x4 points. And on top of it, we have the n bands. So there's 4 indices in this loop calculation, and the data is in this way. So actually, we put the number of bands in the last, number of splines or number of the bands in the last dimension. So it's already in the array, structure of array data structure. So which is which is the main calculation we do inside the code. So you could easily recognize the code here. So it's the loops of the X, Y, Z, then the n bands. So the the innermost loop can be easily vectorized. So the problem is, since the vectors how much minutes I have? 10. Okay. Yeah, it should be okay. The problem is the vectors we collect the result. They are in the original array of structures, so which is not efficient for the memory access. So when you are dealing with vectorization, you must carefully tune your memory access together with it. So the simplest way is you just switch those to SOA. So leave the last index aligned with the coefficients as n. So in this way, you can get very efficient vectorization. And we did it in the past for blue jeans. We are using the same algorithms. You will see, actually, you cannot naively directly do the vectorization. If you do it, you get it just here. This is the time. So as you improve the algorithm, if you just directly do the vectorization, it stops here. But if you could get a better algorithm for the memory access, then you do vectorization, you will reach here. So it's important to tune the memory. And on this KNL, we have those measurements. So they're also 2 paired by 2. So almost on all the platforms, Xeon Phi, you always get speed up by doing this optimization. So we have the chance to look at the bandwidth. So we found through VTune, the read bandwidth really goes to the increase significantly, which indicates actually the computation gets efficient. There's one thing I have to point. You might notice it's great, but at the end, as long as we increase the last dimension and the number of orbitals, number of splines, the performance degrades dramatically here. On most of the systems, KNL, like the regular Xeon, it's less worse, but on KNL or KNC, it's horrible. This is simply because the KNL, KNC system has very small L1, L2, the caches, so it could not cache the result vector, and we noticed that the write bandwidth towards the DDR is higher than we expected, so that's clearly a problem. So the method to solve it is we are not inventing any new method. It's just something happened maybe decades ago. People did just to use it. So the way is to do the cache blocking. I've removed the x dimension, only keep the y, z, and n. So the y, z, n array, then we simply slice them into chunks based on the last dimension. Then Then we just slice the last dimension and put them into blocks. So in this way, actually, you find, so this is without, the block size is the same as the total splines you're here, but when you gradually go reduce the block size, you're able to recover the good performance. Here, we introduce this block size things. You have to tune, but we found actually it's a parameter system size independent, but it's architecture dependent. So like on the KNL, on the regular Xeon and the BGQ cores, you will see similar behaviors of this simply because of the large there's no high bandwidth memory, but a large last level cache. So you mainly just, when you first build your code, do a scan of this parameter and find the optimal one and put it there. It should be sufficient. So here is after doing this cache blocking things, doing the tiling, we are able to recover the performance. You will see that the aggregation goes away. As I mentioned earlier, that we are kind of stuck in this one worker per thread region. So we really need to work work on using more threads to serving a worker. There are significant advances. So from the algorithm perspective, we have the Monte Carlo. So usually we do an equilibration in the beginning, and then we have the calculations. We collect the statistics. When you have more nodes, in principle, you could cut down this part easily. So you have twice the nodes. You just cut your if you only need if your desired accuracy corresponds to a certain number of samples, you double the nodes, you reduce the steps you have to do for each node. You just maintain the total number of samples, your result doesn't change. So in this way, you can reduce your time to solution. However, the initialization part, no matter how many nodes you use, for each individual worker, the time on the initialization is fixed. So you always have to work through those steps. So then it becomes a bottleneck. We can even like we nail those parts into very short region, but those most of the time you are just doing equilibration and you have to trash it. So this is not optimal. As the algorithm goes n cube scaling, the time will be since we have always the wartime limit, so the initialization time will take to huge portions. So we need to find ways to do it, and the way is to just enable the multiple thread working on our single worker. There's another reason. So the computation workload is associated with the number of threads, and also the memory footprint is associated. So the code has the n cube scaling of the memory footprint. So when you do large systems, we found that you get the fat worker problems, and you quickly exhausted the memory. So this is another motivation that we have to do the multi-thread working on individual workers. In this way, just to save the memory, and we can use better the high bandwidth memory. So as previous slide shows, we already have the tiling. So it's very simple. You just put the threading on that loop, just to use the tiles as individual works feeding the threads. And in this way, we didn't see any performance degradation, so it seems well in this first try. We use more like up to 8 threads. No, even on this one is 16 threads. So the throughput maintains the same. So of course, we have to further investigate whether to use nested parallel for or do the task. But from first trial, it seems that it's doable in this way. And by enable this, we found actually the measured read bandwidth almost reached the peak of the high bandwidth memory, and the write bandwidth goes almost to 0, means everything's cached well. So this is the final list of all the performance speed up. So it seems all the optimization schemes are very portable on the 4 type of CPUs we have. Even like from different vendors, like BGQs, everything seems working. Though the performance will be different, but all the algorithms give you significant gains. So you can check those step-by-step performance changes. So this is what we do on the micro QMC, and currently we started to porting those changes to the main QMC code because we really desire those things, especially like the second level threading to improve the time to solution. And with the help with those micro QMC code, we can easily develop improve the code further for the next generation machines. As I mentioned, QMC algorithm is easily parallelized for this reason, so you have you mostly only need to deal with on-node optimization, and so it's easy and simple for us to improve the code. Yeah, that is mainly my talk.
Any questions? Maybe have a minute or two. You mentioned quadratic scaling for the memory per Volcker.
Yes.
And
Matrix is n square, always like that.
yes. So, and per Volcker, you have only node level parallelization. Is that correct?
The workers at first, you have like 10,000, no, you can have about like 1 million workers. First distribute across nodes via MPI. Second distribute on the threads inside the MPI task.
So I was wondering, what is the practical limit for the size due to the limitation per Volcker because of the memory?
Memory?
How large system can you study, let's say, on BlueGenQ here?
Oh, on BlueGenQ, so we have two parts of memory. One is the wave function memory shared among all the threads. It used to be a problem. And the fat worker is the worker-associated memory is also a problem. So on BlueGenQ, I have an example. So I'm able to reduce the, keep only the fat worker dominant. In that case, I'm able to do simulation about 2,000 electrons. So the n square n is the number of electrons. That's the only number matters. Yeah. So approximately 200, 300 atoms.
Does the FFT part become a strong scaling problem?
No, we do only one FFT at the beginning in the initialization. As long as you have the real space wave function is constant. It's just a table you have to check out the numbers. So since we don't do many, the FFT actually we parallelize it by bands. We don't parallelize it like in z direction. It's not necessary. So typically it takes less than 1 minute to do the FFT in most cases.
Okay, one more quick question.
Just to make sure I understand, so is it correct that the whole set of wave functions has to fit on a node?
Yes. Currently, we are doing this. There's just mainly for performance. You have to read it repeatedly again and again, so you have to do it that way.
Okay, let's thank you again.